Hi everyone, my name is Thiago, and along with my colleagues Bo and Yuri, we're going to present adaptive streaming playback statistics dataset work. And I work at Brightcove here in Boston, and we are one of the largest online video platforms. So you can imagine that we have a lot of good quality data that we decided to make tiny sliver available to the research community. And just to give just to give a current state and importance of video, video has been responsible for more than 50% of the internet traffic for quite a few years, um, and video is streamed over a multitude of devices, including like any laptops, desktops, mobile phones, tablets, connected TVs, and any other embedded devices that can play video. Their video is also streamed over a multitude of different network conditions, and all that works mainly because of HTTP-based protocols such as HLS and Dash. I'm not going to go into details of how HTTP adaptive streaming works in this talk, but mainly client adaptation logic can be influenced by multiple factors, including network performance, player size, device decode capabilities, any other QE metrics, um, such as like rebuffering events or buffer level, network conditions, and so on. Um, and as I mentioned, as we are at Brightcove are a online video platform, and most OVPs uh, work sort of like this. This is a very simplified version of a video platform, and on the left side here we have the contribution link. So the camera sending the video feed to an encoder. The encoder spits out different versions of the source video that includes different bit rates, different like rendition heights, uh, creating what we know as an encoding ladder that's used by the players to adapt up and down based on the ABR logic. And those different renditions get distributed to the streaming clients via CDNs. And CDNs play a key role here that they help us save costs in delivery, and they also help us navigate this multitude of different network conditions and stream to a lot of different countries and different conditions out there. And then on the right side, as I mentioned, we have that heterogeneous devices such as TVs, tablets, phones, PCs, and so on. It's important to note here that at every step, there is an arrow connecting that step to analytics. And that's very important because we want to know how the system is performing, uh, come up with optimizations. So the analytic systems of delivery platforms are usually very rich. And I like to just dive into the streaming clients a little bit just to show how much data is collected. Usually, so when a player is loaded or playback starts, um, that those events are sent to analytics. Then at every player event, such as like play, pause, seek, download, full screen, that's all captured and sent to the analytics system. Video view, video engagement, ad start, um, all that is sent to analytics. And the key thing here is that we want to use the analytics as a way to understand um, and measure like volume and audience. So we want to know which content is watched by how many viewers in which country or by which devices, how long the video was played, the distribution of playback times, QE measurements such as the average video quality played, distribution of started times, and QE measurements. It's all this is a long list. It's not limited to just these bullets. But these are just typical uses of analytic systems in practice. What we really want to achieve with this work, and we are listing some possible uses, also again, not limited to just these cases, but it's mostly system modeling optimizations. So in terms of adaptation logic, you can think of ABR algorithms, system performance and improvements. You can come up with new encoding generating ladders or encoding ladder generations, AI machine learning, and so on. This list goes on. And so those are really the objectives of this work is number one, produce a high quality streaming data set that is suitable for the research community. We like to report the metrics that are common across analytic systems. And we also capture several real world, large scale streaming playback events with a diverse set of networks, clients, delivery devices, encoding profiles, and so on. And the intended uses, I went over in the previous slide, but here's a little bit longer list of the same. And next, I'd like to dive into the actual data sets. So we are reporting 4 different events, ranging from a big event with 30 million plus data points, all the way to a smaller event such as almost 700,000 data points. And these events are all different from each other. They, in terms of bit rate, you can see that it varies. Each event is different. So we get mean and maximum bit rate. Resolutions also change with every event is different, and we get different encoding profiles. In terms of renditions, most events use 4, with the exception of event 4, they use 5 renditions. Streaming protocols, we mostly use AGLS and Dash. That covers all Mac and Android devices. Segment sizes, you can see that 2 events use 4, 1 event use 6, and 1 event use 10. So this is one example of a possible research that if you want to study how segment size impacts latency, you have high quality data from like real events. And you also have several device types. So I have TV, desktop, mobile, and so on. And we also are reporting bandwidth. And so in terms of parameters, every time a player is loaded and playback starts, that a session is created. And within the session, say if the customer, if the user watched the video for, I don't know, like 30 minutes, so at every few seconds, the player will send a beacon to the analytics, and that beacon, those beacons are represented by the sequence number. So you can infer the session duration from these 2 parameters. Then we also report like client data, such as like what device in OS that device is, what browser, what player type, player height, rendition height, what codec, segment duration, how many seconds were viewed, how many seconds are buffered, rebuffering count, which is like a very important QE metric, then estimated measured bandwidth. So all these are available for the research community to use. And I'm gonna go very briefly on the statistics itself. I mean, it's all detailed in the paper in interest of time. But we're just showing like a highlight of the event. So we can see that for event number 1, which is the largest one with over 30 million data points, they're mostly TVs and desktops, and with Android and Windows being the most used OSs. And we also just showing network and player resolution. And we cut off, so the network distribution goes beyond 100 megabits per second, but we cut off just for presentation purposes. And I just also like to give one like brief insight of how to read this data. So you can think of this peak as like just under 600 pixels. That will be enough to pull rendition number 3. But that depends on the ABR algorithm decision making, right? Because that although the player height might be enough, the network conditions or buffer size might not satisfy the condition to pull the highest rendition. And then similarly for event number 2, there's a similar distribution of devices, network, and player heights. For event number 3, what I can say here is that because it's mainly desktop and Windows, you can infer that this peak is because the video is mostly embedded in a web browser with a low, a small height. And so that explains this peak. And finally, for event number 4, it's a subset of a larger event where we are only showing Windows desktops. But the interesting thing here is that we have 5 renditions. And if I'm not mistaken, I think the segment size here is 10. So every event is different. There's a lot of data to play around. But I also want to give another example of a use case. So we just watched, we just saw data for event 4, so where we have distribution of player sizes and bandwidth. So we can see here the adaptation to player size. As the player is small, the rendition pulled will be the smallest one. And then as the player increases, as the player height increases, we start pulling larger and larger renditions until we get the largest possible one. And then similarly for adaptation to network bandwidth, as bandwidth is small, the player will request the lowest possible rendition. And then as bandwidth increases, the player starts switching up until it gets to a point where around, in this case, around 3 megabits per second, the player does not necessarily pull the largest possible rendition. And that can be for a variety of reasons. It can be, for example, that the player doesn't have enough buffered content, or player size might not be big enough. So a higher bandwidth does not necessarily mean that it's going to pull the highest possible rendition. So the key observation here is that bandwidth adaptation is no longer the only dimension for the problem. And so with that, we can devise a very simple client model where we have a step function for adaptation to bandwidth and similarly for player size. I'm not going to go into details here again in the interest of time, but the details are explained in the paper. But when we combine them, we can come up with, we pick the minima here, and we come up with a rendition selection logic that is sort of very reliable in terms of when we compare to the real world, in terms of observed and what we modeled. And this is a very simplistic model. So, but we believe that with the data that we put available, folks can come up with more sophisticated modeling clients and systems. Our data can be used to train some machine learning or AI models, create optimal design of streaming clients, some analysis of performance of data streaming systems, ABR algorithms, content-aware encoding optimizations, multi-screen delivery, and this is just one use case of the data with the data we put available. We believe possibilities are a lot. And with that, I'd like to conclude, and thanks for your participation.